In the previous section, we defined a derivative to be the slope of the tangent line at any point along a curve, and of course that point had to be defined. So let's go ahead and review that real quick. It's the slope of a tangent line at any point, and I'm going to just say any defined point along a curve. Now, keeping this in mind, if we talk about the slope of the tangent line in this way as a derivative, we should be able to look at a graph and get an idea whether we have a positive sloping tangent line or negative sloping tangent line based on the graph. Now, some notations again we use for derivative. We used f prime of x. We also used dy dx. I think we had some other ones, d sub x, something similar like that. So we'll see some of these common notations as well. Another one we saw was y prime. So we'll be using these all interchangeably. Now you can see that when we were working with finding the derivative using the limit definition of the derivative, it got a little bit long. So let's go ahead and look at the limit definition of the derivative. F prime of x was equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. So this was how we found the derivative, and this is the limit definition of the derivative. Now if you work through these problems, you can see these got very long and pretty complicated sometimes, lots of algebra. We never even really did any trig functions with this either. And so you kind of have to wonder, well, how do we take derivatives of trig functions? And that is coming up. But that's some of the limitations of using this limit definition. It's tedious, it's long, there's a lot of room for error. So what we want to do is we want to look at some shortcut rules for differentiation. Now with these shortcut rules, these save a lot of time, and they're pretty accurate too, because people are more consistent when they use them because there's less algebra involved. So these rules for differentiation are shortcuts. Now remember, the derivative is the slope of the tangent line, so those are kind of few things we want to keep in mind. Our first rule is called the constant rule, and it basically says the derivative of a constant is 0. And we'll write this out as well. So the derivative of a constant is 0. And I'll show you why this is in a second. Let's go ahead and write this out in notation wise. So if c is a real number, and it could be a decimal, it could be a fraction, it could be an integer. It could also be a number like pi that's represented by pi or e. But if c is a real number, then what we know is the derivative with respect to x of c equals 0. So the derivative of a constant is 0. Now why does this work? Well, let's go ahead and write out a constant as an example. So let's look at the function y equal 2. Well, if we were to sketch that Cartesian coordinate system, here we're going through y equal 2. This tangent line is the line itself. So right on top of here is the tangent line, and the slope of the tangent line is equal to 0. It's a horizontal line, and so the slope of the tangent line is also horizontal. So that totally makes sense that the derivative of a constant is 0. And again, this could be a fraction, it could be a decimal, it could be a number like pi or e. That's the derivative of a constant, so that's our constant rule. Our next one we want to look at is the power rule, and this is one that you'll be using a lot. Now the power rule takes into account a polynomial expression. So if we have some sort of an exponent, so if n, and we'll call n as going to be our exponent here, now in this first iteration of the power rule that we look at, we're going to look at if n is a non-negative integer. Now non-negative means it could be 0 or it could be positive. Now eventually we'll extend this rule to negative integers as well, and even to rational numbers, and then finally we can actually get up to rational powers as well. But for now, we're just going to look at non-negative integers. Then what we have is the derivative with respect to x of x to the n is equal to n. I bring that exponent out front, and then I drag along my base and I decrease the exponent by 1. So that's my definition of a derivative. Now this is a pretty slick little rule. You can always establish this rule using the difference quotient, the limit definition of the derivative from up above. But we want to look at quite a few different examples here. So for example, let's look at the derivative with respect to x. And we can write quite a few different values here, but let's go ahead and start with one like x to the 9th. So the derivative with respect to x of x to the 9th. So using my power rule, I bring the 9 down, and then I decrease the exponent by 1. So this simplifies to 9x to the 8th. Okay, so that's a lot easier than applying the limit definition of the derivative, because you would have to take x plus h quantity to the 9th power in order to figure this out using that limit definition of the derivative. Now this still has the same meaning. This is still the slope of the tangent line at any point along the curve. So this implies that f prime of x is equal to 9x to the 8th then. Or y prime equals 9x to the 8th. These are all the different notations that we can use for that. Now this notation over here on the far left means the derivative with respect to x of x to the 9th. So this is kind of our problem. This is our answer over here. Let's go ahead and look at a couple other ones. Let's go ahead and look at x to the 1st, or just x. This one's a bit of a trick. So the first thing we would want to do with this one is when we don't have anything in the exponent, it's an implied 1. So let's go ahead and rewrite this as an implied 1. So using that power rule, what we'll do is we'll bring the 1 down, and then we'll decrease the exponent by 1. So I get 1 times x to the 0. Now recall from our previous work with exponents, anything to the 0 power is 1. So I'm left with 1 times 1, which is 1. So what we have here then is the derivative of x is 1. Now we're going to take this rule and expand it a little bit further to any coefficient out front of x. And remember, out front of this x there's a 1 for our coefficient. But what do we do if there's a 9 or a 10 or a 12? And we'll come up with a rule here in a minute called the constant multiple rule. Let's go ahead and look at another one that comes up as a bit of a trick. Let's look at the derivative with respect to x. And in this case, let's go ahead and look at 2 to the 8th. Okay. Well, 2 to the 8th, you'd think, okay, I'm going to bring the 8 down, decrease the exponent by 1, but that's not what's going on here. If you notice on all of these, I have a base that this is a variable, and this variable matches my differential on the bottom, dx. So the variable matches the dx on the bottom. So this is a constant. It looks like an exponent, and it is an exponent, but it's a constant. It's not a variable to an exponent, it's a constant to a exponent. So it's a constant to a constant. And we know that the derivative of a constant is 0. And that was, again, from our first rule that we looked at, which was called the constant rule. So you kind of have to be prepared for some of these bits of complicated type of problems that look really straightforward up front. But you want to stop and pause and look for a variable in some of these and realize that they're a constant. Next one we're going to look at is a constant multiple rule. Now with the constant multiple rule, we're basically saying, well, what do you do if there's something out front of the variable? You know, what do we do that? And I don't know why I wrote year. Rule. Constant multiple rule. So if we have a constant out front of a problem, what do we do with it? So our rule would say if f is differentiable, so we have to have a differentiable function. So if my function is differentiable and c is a constant, what would I do if I took the derivative of c times f? And then what we know then is the derivative with respect to x of c times f of x is equal to c, my constant, times the derivative of my function. So basically, to me, when I look at this, I think just drag along the constant. That's all that you're doing here. So let's go ahead and look at a few of examples that could match this type of problem. Let's look at the derivative with respect to x of negative, let's do 7/8 x to the 12th. Now, usually when you get to working these problems, they're going to be pretty straightforward. You'll just bring the 12 down, decrease the exponent by 1. But for here, I want to think about rewriting this. So I'm going to show some more steps than you're probably used to seeing. So to get started, the constant multiple rule says I can take the constant that's out front and pull it clear out front of the derivative. So I could pull this out front, negative 7/8, and then I'm left with the derivative with respect to x of x to the 12th. That's what I'm left with. So dragging that along, negative 7/8, you'd bring the 12 down and then decrease the exponent by 1. So simplifying, I'd have negative 7/8 times 12, so 8 divided by 4 is 2, and 12 divided by 4 is 3. So it looks like to me we're left with negative 7 times 3 is negative 21 halves, because I have a 2 in the denominator, x to the 11th. And there's my solution. Now a lot of times you won't show all of these steps. You'll kind of just take the derivative without showing this intermediate step, and that's okay, but you have to be able to show all of these parts where you have the coefficient out front. So let's go ahead and look at another example. Let's look at the derivative with respect to y this time. And it just has to do with whatever our variable is of interest. So let's look at the derivative with respect to y of 3/8 times the square root of y. Well, wait a minute. We never said anything about eighths. So I'm not sure what we should do with that. Well, let's go ahead and split it into two parts. So I'd have 3/8 times the derivative with respect to y of the square root of y. So that would be our first rewrite. Now I don't have any rules about derivatives of radicals here, but my rule would be, well, let's rewrite it. So I'm not taking a derivative yet. I'm just rewriting this with a 1/2 in the exponent. Now your book doesn't show you this rule quite yet. It says, well, you remember from last chapter that when we took derivatives using the limit definition of the derivative, this is what we got for an answer. But I want to show you the shortcut rule here too. So this is equal to 3/8. Now, to take your derivative, the derivative portion, you'd bring the 1/2 down and then decrease the exponent by 1. So you bring the 1/2 out front, so you drag along the 3/8, bring this 1/2 out front, decrease the exponent by 1. So nothing cancels here, so it looks like to me I'm left with 3 times 1 is 3, 8 times 2 is 16, so 3/16 y. 1/2 minus 1 is a negative 1/2. So this is a solution, but it's not the solution, because remember, we never leave negative exponents. So I would flip the y to the negative 1/2 into the denominator, and it would become a positive 1/2. And my final step would be rewriting this from exponential form to radical form. So here's my simplification. Now remember, this has the same definition as usual. This is the slope of the tangent line at any point that is defined on this function. So I can still use this to find the slope. These are all my derivatives. Next thing I want to look at is called the sum rule, and it could just as well be called the difference rule, because it's basically saying the derivative of a sum or a difference is just the sum or the difference of the derivatives. So this could be called the sum or the difference rule. Now a lot of these rules, even though we're formally writing them out, we don't necessarily think about them when we're taking derivatives, because it seems kind of like a natural thing to do is to just go ahead and take the derivative of each component of a function. So what this says is the derivative of a sum or a difference, so I'm going to put the plus or the minus, is equal to the derivative of the sum or the difference. Okay, so again, the derivative of a sum or difference is a sum or difference of the derivative. Well, it sounds more complicated than it actually is. Let's go ahead and look at an example where we're taking the derivative with respect to x. And for this one, let's go ahead and, we'll keep with an x here. Let's do 12x to the 5th minus 13 I have a lot of stuff showing up on my screen here. 13x to the fourth plus 7x squared plus 2x plus 5. Actually, let's make it a minus 5, so we have some minus signs in here as well. So I'm taking the derivative of all of this, so I need to make sure I have parentheses around it. And then I go ahead and I just apply the sum or the difference rule. So this is going to equal to 12, and then I'd bring the 5 down, decrease the exponent by 1. Then I have a minus 13. I bring the 4 down, drag along the base, and then decrease the exponent by 1. Drag the 7 along, that's my constant multiple rule. Bring the 2 down, decrease the exponent by 1. I have my 2x here, so I drag along the 2. I bring the implied 1 down and decrease my exponent by 1. Because remember, this is an implied 1. Now with my constant, I could remember my rule, the derivative of a constant is 0, or I can remember that this is actually x to the 0. So another way I can rewrite this one, let me write this off to the side, negative 5x can be implied as negative 5 can be rewritten as negative 5x to the 0. So if I think about it that way, I bring the 0 out front, decrease the exponent by 1. So when I rewrite, I have my derivative is equal to 60 x to the fourth minus 52 x to the third plus 14x plus, here I have 2 times 1 is 2, 1 minus 1 is 0, x to the 0 is 1. And then for my last piece here, negative 5 times 0 is 0, 0 times x is 0. So I'm done. This is my derivative. Now remember, this is the slope of the tangent line at any point along the curve. Now we also have things called higher order derivatives. And in this section we learn how to find higher order derivatives, but we don't really define what they're useful for quite yet. But I will tell you that they're useful when we're looking at concavity of graphs, meaning does a graph open up or does it open down? Does it have a max or does it have a min? Does a function have a max or a min? So these are all different characteristics that we're interested in eventually finding. But for higher order derivatives, the first thing will probably be the notation. So let's go ahead and look at some notations. One that you'll see is, of course, for first derivative, we used a notation like y prime or f prime of x or dy dx. These are just some common notations. Now what about for a second derivative? Well, what you do to find the second derivative is you find the first derivative first, and then you take another derivative to get to the second derivative. Well, our notation here is y double prime f double prime d squared y dx squared. Okay, and that's from taking the derivative of the derivative, and so that's why I end up with the d squared y dx squared. Third derivative, I would guess that you could probably come up with what the third derivative will look like. It's going to look like y triple prime f triple prime. These are all, these prime marks that we have here are keeping track of the number of derivatives. This would be d cubed y dx cubed. And then of course fourth derivative we'd have y fourth prime, but that notation gets a little bit cumbersome, so we start switching into thinking about Roman numerals, or there's another way we can write these as well. So fourth derivative. And there's more notations than just these. These are just some of the common ones that you might see. So a lot of times after we get working on these, we start rewriting these instead of y quadruple prime. Sometimes we would write y and then the 4 would be in parentheses. It doesn't mean y to the fourth, it means the fourth derivative. So that's the same thing that you might see here with our f4, fourth derivative, f4 of x. And of course d4 y dx to the fourth would be something you could see here as well. So you can see this progression, and a lot of textbooks use Roman numerals here, so they might use an IV for fourth and a V for fifth. Well, let's go ahead and look at some higher order derivatives, And basically, just as we said, once you start taking derivatives, you just keep taking derivatives until you get to the order that you were looking for. So let's go ahead and look for d cubed y dx cubed of, actually I don't need a y there if I'm going to put my function here. And let's look at x to the 5th minus 2x cubed plus 4x plus 1. Okay, so to get started, what we do is we look for y prime first. Now if I want to use my notation, I could use d dx, but I just want to kind of keep track here of what's going on in an easier way. So my original function I'm going to rewrite as x to the 5th minus 2x cubed plus 4x plus 1. Y prime then would be 5, bring the 5 down, decrease the exponent by 1, drag the negative 2 along, decrease the exponent by 1. Now remember, this is an implied 1, so I'd bring the 1 down, decrease the exponent by 1. And then also remember, for this 1, that's really 1 times x to the 0. Anything to the 0 power is 1. 1 times 1 is 1. So here I would have plus, I'd have 1 times 0, x to the 0 minus 1. Okay, so y prime, we still haven't found y double prime, we're just still on our single prime. So I'll have 5x to the 4th minus 2x squared, 3 minus 1 is 2, plus 4. 4 times 1 is 4. Now what is x to the 0? X to the 0 is 1. So 4 times 1 is just going to be that 4 again. Now over here for my last one, the derivative of a constant is 0, and I can see that I get a 0 here. So that's the first derivative. Let's go ahead and look at the second derivative. I just follow from the first derivative, so I have 5 times 4, decrease the exponent by 1, minus 2 times 2, decrease the exponent by 1. And then I see I have a derivative of a constant here again. So I can think about this as 4x to the 0. So this is 4. I bring the 0 down, decrease the exponent by 1. So 5 times 4 is 20x cubed minus 4x to the first. And of course this whole term goes away because it's the derivative of a constant again. So our third derivative, y triple prime, or if you wanted to do y third derivative in this notation, you could. So I have 20, I bring the 3 down, decrease the exponent by 1. I bring the 1 down, decrease the exponent by 1, because remember that's an implied 1. And when I simplify that third derivative, I have 60x squared minus 4. 4 times 1 is 4. 1 minus 1 is 0. X to the 0 is 1. So this might be my third derivative. Now I have to go through the other derivatives to get to the third derivative. I can't really skip through, and we just hope we don't have to find things like the 20th derivative. And there's really not a lot of usefulness for the 20th derivative, although it's interesting to see the patterns involved in actually finding that value. So that's an example of higher order derivatives. This is a pretty short little section as long as you get these rules. They're definitely ones that you'll want to have memorized. We'll be using them all the time. If you have any questions, please let me know. You can use your Pearson Connect. You can also send me a screenshot of your problem or your work, and I'm happy to help you that way as well. Good luck.